Okay, very good. All right, moving on to section 3, we're going to talk about types of data. And we talked last time about the difference between the population versus the sample. The population is the group that we want to study. Everybody that we're considering as a part of our conversation or study. Usually the population is too large for us to get our hands on, so we use a sample, which is a sub-collection of the population. Numbers that describe a population are called parameters. Okay, a numerical characteristic of the population. And since we generally can't put our hands on the population, we say that population parameters are generally unknown. Okay, population parameter is usually unknown because we can't get our hands on the population. So how can I get my hands on a number that describes the population? And remember last time I told you that that's one of the large parts of statistics, is we're using the sample to try to help us figure out what these population parameters are. Okay? Versus a statistic. This is a different definition from statistics that we talked about the other day. We talked about the general field of statistics, but now we're talking about a statistic. This is a numerical characteristic of the sample. So when we look at numbers describing a set of data, something we should ask ourselves is, did this come from a sample or did it come from a population? Okay, if it's from a population, that number would be a parameter, population parameters. If it's from a sample, the number is a statistic. It's a sample statistic. Okay? All right, so we've got determine whether the given value is a parameter or a statistic. Okay, as of January 2007, 44% of the governors of the 50 states in the United States are Republicans. Would this be a parameter or a statistic? And I guess in this case we were talking about the 44%. Okay, it's a parameter. We've got 50 states. That makes up a population. Right, that's everybody that could be a governor, and so this 44% describes the population. It's a parameter. All right, the next one, among the flights included in the sample of flights in data set 15, Appendix B, 21% arrived late. Would that be a parameter or a statistic? Okay, that's a statistic. Okay, because, you know, obviously, well, we hadn't looked at it, but they even said it. It's a what of flights? Sample of flights. It's not all of the flights. Who needs the handout? What was that? Excuse me. Pardon me. Thank you. Okay, statistic, which apparently I cannot type. Okay. All right, statistic. Okay. The average or mean atomic weights of all elements in the periodic table is 134.355 unified atomic mass units. Parameter or statistic? Okay, parameter. Very good. All right, any questions about parameter versus statistic? Don't forget this, okay? Got the final exam at the end of the semester, so we got to keep all of these things in mind. You want to go back over them. And even more importantly, when we get to the end of the course, we'll be doing a lot of hypothesis testing. And again, the whole point of that is to use sample information to make inferences about the parameters. And so you need to, be able to distinguish between the two. Okay? All right, types of data. We have quantitative or numerical data, versus categorical or qualitative data. That pretty much tells the story. Quantitative data is something that's a numerical measure or count. Okay, it has to be a numerical measure or count. Not just digits. Okay, digits don't necessarily make it quantitative. If those digits have no numerical meaning, then, you know, it's not quantitative. Versus qualitative is really just a label. There's no numerical meaning. What are some examples of quantitative data? That we might collect? Was it? Birth dates? Ooh, that was kind of funny. I don't know about birth dates, but age would be one. Okay, definitely. Okay, anything else? Okay, all right, what about the time it takes you to travel to campus? All right, the amount of time it takes you to do something. Okay. Someone else said something? Okay. All right. The number of students, okay, in sections of Math 120. Okay, very good. Those are very good examples. All right. Categorical. What are some examples of that? Okay, very good. That's one that includes digits but doesn't have any numerical meaning. Social Security number. It's a label, right? Okay, what else? Okay, student ID. All right. Again, digits, but that's good. What about something without digits? Okay, username. Favorite color. Program of study. Car type that you drive or prefer. Okay, all of those things are categorical. They're just labels for our, identifying something about an object. Okay? Very good. So let's see if we can identify whether or not these things are qualitative or quantitative. The daily high temperatures for the month of July, that would be what? Quantitative. Okay, temperature is numerical. Okay, it's quantitative. The player numbers for a soccer team, qualitative, just the label to identify the player. 20-second pulse count, quantitative, excellent. And zip codes in Richland and Lexington counties, qualitative, excellent. Okay, is that the last one there? Yes. Okay. Now we can further break down our quantitative data into two more categories. That is discrete data versus continuous data. Okay, discrete data really is counts or countable. Okay, things that we would normally count, that makes up discrete data, and there's a finite number of values that it takes on. Or a countable number. This is where I really should have said that. Okay. Things that we would normally count are discrete data. Okay, like the number of students in this class. That's something I would count. the number of bad checks drawn on a bank in a day. Okay, that's countable. Versus continuous data is data that we measure. Okay, and usually with continuous data, those values can take on an infinite, or those variables, I should say, can take on an infinite number of values. Okay, continuous data can assume an infinite number of values, okay, instead of a finite or countable number of values. Okay, so what are some things that we usually measure instead of count? Weight, okay? All right, you don't have to weigh just 120 or 121. You know, you could be 120.27839, you know, it goes on and on and on. So it's something that we measure, it's something that can take on an infinite number of values. All right, anything else? Okay, weight, height. Anything else? Temperature, very good. Okay, what about gallons to fill your tank? Okay, oops, that went off the screen. But the gallons to fill the tank, that would be continuous data. Okay? Alright, so we've got some examples here. Determine whether the given values are from a discrete or continuous data set. And I wanted to say about the gallons to fill a tank. When we decide whether or not something is continuous, we don't look at the measuring instrument. Okay? We think about the values that it could take on independently of the measuring instrument. Okay, for instance, I can't think of an example. Let's see. If we're talking about weight, you know, and let's say your scale goes to the first decimal place. All right, you go down to buy low and you get bags of potato chips off of the shelf because you're tired of getting a half empty bag and you want to know if it really does have a pound of chips or whatever. Okay, well, your scale's not going to pick up on the nuances and differences from one bag to another because the scale is not sensitive enough. Okay, it might show 1 pound every time. Do we think that it would be 1 pound every time? No. Okay, we need a scale that's a little more sensitive that can pick up on the differences between it. And we have to think about, does it have to be 1 pound or 2 pound? No, it could be 1 point whatever. Okay, so think about that sometimes when you're deciding if it's discrete or continuous. Okay, Honda Civic has 4 cylinders, discrete or continuous? Discrete. Okay, I don't know much about cars, but I think that's something that we can count. All right. George Washington just decided to change his name. Was 188 centimeters tall. Is that discrete or continuous? Continuous. Okay, nice round number, but it's possible that it could take on any value within a certain range of values, right? 0 to whatever the tallest person is. Okay, when a Cadillac STS is randomly selected and weighed, it is found to weigh 1,827.9 kilograms. Discrete or continuous? Continuous. Very good. Okay, and is that it? Okay, the volume of cola in a can of regular Coke is 12.3 ounces. Okay, continuous. And the cost of a Snickers candy bar, this is a sneaky one, at a gas station is $1.09. Discrete. Okay, discrete. Continuous and discrete, the difference isn't just decimals. We really have to think about are there gaps between the values that it can take on? If there are gaps, it's discrete. Okay, that candy bar is not going to cost 1.095, like we've been describing before. It's going to be $1.09 or $1.10 or $1.11. So there are gaps between there. All right, but whatever the values are, they are countable. Even if it takes me from now to the end of eternity to count, I can count the possible values that this price or this Snickers candy bar could take on for cost. Does that make sense? So this is actually discrete. And we said continuous here. Okay, questions about that? All right, very good. Okay, another way for us to, actually let me pause this. Stop this. Another way that we can classify our data is by looking at levels of measurement. There are 4 levels of measurement that we're going to talk about, and they are a progression. When I'm looking at a variable or some item and I want to decide if it's nominal or ordinal or whatever, I kind of start at nominal and work my way up. Okay, nominal is probably the simplest level, and the last one that we'll talk about is ratio. It's most difficult. Okay, when we talk about data that's at the nominal level of measurement, this is data that simply has a label. It has no numerical meaning. Okay. So things again like name, program of study, the state in which you were born. Okay. Those things are all nominal. All right. Those are examples of nominal level data. So pretty simple. That's the whole story on nominal. All right. The next one is ordinal level of measurement. Ordinal meaning we can put things in order. So here we can put data in order. But we cannot calculate precise differences. Okay, we can put the data in order, but we can't necessarily calculate precise differences. This is the only level of measurement, I'm not sure if the author said this or not, that can take on qualitative or quantitative data. Okay, so some examples of ordinal level measurement would be, and I should use this word here, I mean rankings, that's what we're talking about. We can put it in order as far as, this one is better than another. So ranks of football teams, dare we mention that today? Go Tigers, that's right. All right, ranks of football teams. Let's see, what are some other things? Ranks of a hotel or a restaurant or a product. The grade, right? Our grades, your grades? Yes, letter grades. Not number grades, but letter grades. A is better than B. B is better than C. But without knowing more, we don't know the precise difference. If one student gets an A, the next one gets a B. Could be a difference of 1 point, or it could be a difference of as much as 20 points, right? So we do know that the A is better than the B, but without additional information, we don't know what the difference is. We cannot calculate precise differences. Anything else that might be ordinal level measurement? Placement in a race. First place, second place, third place. Okay, we know that first place is better, but again, it could be a fraction of a second, or it could be a long, long, long time. That's the difference. What's that? Sizes. Okay, all right. Very good. Excellent example. Okay, or another one similar to that is rankings of poor, fair, good, great, superb. Okay, all of those are things that we can put in order, but we don't calculate the precise differences. Okay. All right, the next one is interval level of measurement. So we can put these in order. And we can calculate precise differences. So you see now why I say this is kind of a progression. Okay, this one has something a little more than the ordinal level. Okay, but what it doesn't have is a natural or inherent zero. And I'm going to tell you what that means. And additionally, ratios are meaningless. Okay. So what about that natural or inherent zero? Generally, when we think of zero, what does that mean for us? Nothing, right? However, sometimes zero is just another value on a scale of values. For instance, temperature. Okay, if it's 0 degrees, does that mean it can't get any colder? No. Okay, so temperature is an example of ratio, or rather interval level of measurement. Okay, 0 means nothing, and if I talk about, okay, today it's 90 degrees, and hopefully in a few months it's going to be 45. Okay, then do we say today is twice as hot as it will be over in December? We don't really say that. It doesn't really mean that, right? When we think about what the number represents. Okay. Furthermore, if we change it from one scale to another, it's no longer twice as hot, right? The ratios just don't make sense. So not a lot of things at this level. Temperature is one. The year, calendar year. Okay. Not your age, but the calendar year. Okay. If something happened in the year 2000, and then we want to compare that to the year 1000, does that ratio make sense? Do we say the year 2000 is twice as much? Do we have a natural zero? What does the year 0 mean? Is that the beginning of time with our calendar? No, it's not. So there's no natural zero. So calendar year is another example. Okay, and there are a few others, but these are probably two of the most common ones that we will encounter. Okay, questions about that? And then finally, the ratio level. We can put the values in order. We can calculate precise differences. We've got a natural zero. 0 is kind of the beginning of the counting process. You got to start at 0 and go up, and the ratios make sense. Okay, values can be ordered. Precise differences can be calculated. We have a natural zero, and ratios make sense. Meaningful ratios. And there are all kinds of things like this, like salary. Okay, it makes sense to say one person makes twice as much as another. Okay, what are some other things? Age. Okay, Length, okay. Weight keeps coming up. Pressure, okay. Let's clarify pressure a little bit. Okay, air pressure. I don't know a lot about air pressure, but I think that's right. Someone else said something. Class times? What do you mean by that? Okay, length of your class. Okay. Length of time. Okay, for class. Very good. All right. Very good. Questions about these levels of measurement? Okay, you're going to go home and you're going to think more about it. But we got a few examples here. Okay, we got the 4 levels of measurement. We want to decide which one is appropriate for the data that's described. The type of movie, nominal. Okay, the type of movie would be nominal. Just a label. We can't say that dramas are better than comedies or anything like that. Okay, actual temperatures in degrees Fahrenheit as listed in data set 11 in Appendix B. Interval. Okay, and they did mention in degrees Fahrenheit. Is there a scale that might not be interval level data? Kelvin, right? There's supposed to be the absolute 0 that they found. That's the 0 on the scale, and it goes up there. So if we have temperatures measured in Kelvin or kelvins, then that would be ratio level data. Okay, but generally when we think about temperature, we're thinking either Fahrenheit or Celsius. All right, measured amounts of greenhouse gases in tons per year emitted by cars, listed in data set 16 in Appendix B. Ratio, very good. And ranks of cars as evaluated by Consumers Union. Ordinal. Excellent. Alrighty.